I was taught when I was young to start immediately to introduce what is the main concept that we are talking about. So I will do, and for our purposes, a superimposed code is a binary matrix with the following property. For any column that you can choose, and for any other k-1 columns, you can always find a row in the matrix such that the column that you have chosen as a 1 in this row, while all the other k-1 columns have all zeros in this column. So this is the pattern that characterizes superimposed code. You have this matrix, and you can always, for any column and for any other k-1 column, find a row such that you find 1 here and everything is 0. Why adult people should be interested in this simple object? Well, it turns out that we have to. Actually, this idea is very old. Probably was born before all of us. In fact, in 1951, Calvin Morse introduced this idea in the context of information retrieval. Actually, Morse was also the one that introduced the expression information retrieval, and is also very well known for the Moore's law, which is the other Moore's law, which essentially says that an information retrieval system will be used only if it is easier to use it than find directly the information that you are looking for. Anyway, this idea of superimposed code has been rediscovered many, many times. For instance, by Kautz-Singleton, and usually in the information theory community, this is the paper that everybody quote about the introduction of superimposed code, because people don't know history in a certain sense, was rediscovered by Erdős, Frankl, and Furet in another context in 82, and was also rediscovered by Wang and Soch in the context of group testing in 86. And not only that, but it was also rediscovered many, many other times in many different concepts. And I will briefly explain why this simple concept keeps popping up in many, many papers. Well, the main reason is that it finds an astonishing variety of applications. Superimposed code are used in computational biology, in modern one-bit compressive sensing, in data security, in coding theory, distributed computing, and many other problems. In fact, when Christian asked me, well, you want to do an overview of application of superimposed code, I said, well, good, you are inviting me for a semester. No, he said, I'm inviting you for half an hour talk. Okay, I will talk also essentially of my last result on the area. Anyway, I will be happy. But when I speak about applications, I mean real applications, not the application that we like to put in the introduction of our paper to trick the referee. No, real applications. For instance, during the epidemic, the COVID-19 epidemic, superimposed code were used to do fast testing of a population. And essentially, the idea was to pull together samples of saliva in a single part, test them, and do group testing. And the decoding phase was made using superimposed code. Anyway, but there are many other real applications of a superimposed code. Anyway, I'm talking I will be talking about two applications, as I said, application to multiple access channel and secure fingerprinting. Let's see first why superimposed code appear in the area of multiple access channel. When we explain our student the problem of multiple access, we usually use different examples, for instance, the Ethernet or waveless LAN or satellite communication, whatever. Essentially, these are examples of what people like to call cocktail party multi-access communication. What happens in a cocktail party? That lots of people talk together and the listener here do not understand anything. Why? Because when people speak at the same time, we get confused and we do not receive information and all the information is lost. And this creates problem. This is the basic, one of the basic problem in multi-access communication. Because when there are simultaneous transmission, there are collisions, failures, and so the information gets lost. So what is one of the basic problem in the area? One of the basic problem is to find a deterministic protocol, so no probabilistic. We are not speaking about the classical ALOA system in which station transmit randomly, hoping that sooner or later there will be only one transmission successful. So deterministic, non-centralized, so that there is no special guy that tells you can transmit, you stay silent, and so on. So no centralization. And non-adaptive, what does it mean? That stations cannot listen on the channel and understand whether or not their transmission has been successful. So they are completely oblivious. This is the most hard problem in the area of multi-access because we cannot make any hypothesis. And under this hypothesis, we want to find a protocol that allows each station to transmit successfully. Let's make an example to see how superimposed code can be useful in this situation. The idea is very simple. Suppose that we have a bunch of users, bunch of stations. What we do is the following. We assign to each station a code word of the superimposed code, which is a string of zeros and ones. And now we instruct the station to interpret a zero as stay silent, do not transmit. A one, you can transmit, okay? Now suppose that there are three stations that want to transmit, for instance, this one, okay? So what they do? They start reading their protocol, the string of zeros and one, and if they see a one, they transmit. If they see a zero, they stay silent. What happens? Well, for instance, in the first transmission, all three stations transmit, and there is a failure. Because when there are transmission at the same time, nobody understands. In the second unit of time, you will see that only the second active station is allowed to transmit, so there is a success. There is a success also in the third unit of time, because only the third station is allowed to transmit. There is a failure, because all three stations try to transmit. There is another failure. And finally, the first station finds a particular instant in which it transmits alone. And so there is success. So you will see that the protocol works, and why the protocol works because of the basic property of superimposed code. that I remind you means the following. For any, in our case, station, there is a unit of time in which the station transmits and all the others stay silent. And so this means that any station will find an instant of time in which it transmits singly, and so everything is okay. So superimposed code gives a strategy that we were looking for. What is the problem? Well, the problem is to construct codes with this property. And the basic parameter is the length of the code must be as small as possible. Why? Because the length of the code corresponds to the number of attempted transmission. And we want that the protocol terminates as soon as possible. In general, T is the relevant parameter in all the applications that I discussed before. Everybody wants to find a superimposed code with a short length, okay? What is known? The first bound is the following. Always there exists a superimposed code with length upper bounded by k, if remember, k is the number of allowed station by k squared log n. So it's logarithmic in the number of stations. And this is important because the huge number is the number of stations, while usually k, the number of active stations, is small. And this is a bound that was found by Erdős, Frankl, Furedi in 82 by the probabilistic method, and independently by Wang and Soch using an exponential time algorithm. So actually, they are not algorithms. They are proof of existence, but they do not give you an algorithm because nobody wants to use an exponential time algorithm. Is this bound good or bad? Well, it's quite good. Oh, by the way, as usual, it was rediscovered many times and not always in the best form. This is terrible. Anyway, the bound is not too bad because Dyachkov and Rykov in 82 proved that there are no superimposed code with length smaller than this quantity. So you see the upper bound and the lower bound differ by a logarithmic factor in the denominator, okay? The proof by Dyachkov and Rykov, well, it's safe to say that nobody understood. Human understandable proof were given by Rusinkov, easier proof by Furedi, and another easier proof by Alon and Azotti. Anyway, so this is the difference between the upper bound and the lower bound on superimposed code. Closing the gap is very difficult because it is related to a famous open problem by Erdős on the maximum size of a so-called cover-free family. That is, what is the maximum size of a family of subset such that no set is included in the union of other k minus 1. This is a problem that Erdős posed in the 80s and is still open, essentially. Anyway, another important problem, another important result is the first efficient algorithm to construct superimposed code with almost optimal length. So with the length k squared log n. And this was given by Porat and Rothschild on the IEEE transaction information theory in 2011. Okay, let's go back to the basic motivation to introduce superimposed code in the context of multi-access communication. If you remember what we do, we assign a code word to each stations start together and they execute the protocol. And this is the basic assumption. But this, and the other assumption is that most k-users are active, a transmission succeeds if and only if in a given time instant only one station is transmitting. But in realistic scenario, the first assumption does not hold. There is no reason to assume that all stations start at the same time. For instance, suppose we consider a bunch of sensors that have been deployed in an area. No? Usually sensors are sleeping all the time because they want to save energy, okay? And in random time, they wake up and start transmitting. But there is no synchronization between them, okay? It's impossible. And this is the model that it is usually the model that everyone uses in a classical paper by Massey and Mattis on the IEEE transaction. And also the basic property that I told you before is very weak, because in noisy scenario, you can be unlucky and maybe just in that instant of time in which a station could transmit successfully, some terrible thing happened, and so you get lost in the transmission. So it's not sufficient. Because maybe in that instant of time, the station is not working properly, for instance. Let's see what happens when the first assumption does not hold. That is, when the stations do not wake up at the same time. Okay, if you remember well, in the basic assumption, all three transmissions worked perfectly. But for instance, suppose now that the first station wakes up one time instant after the other. So essentially, when the other station started transmitting, the station is still sleeping. So it starts in this time. But now the protocol does not work anymore, because you will see. Let's go back. Because now this station is colliding with the other. And so the protocol does not work. And so we need something stronger, another property. So we need actually two stronger properties. The first property is that the basic property of superimposed code must hold for any cyclic shift of the protocols, because the fact that it holds for any cyclic shift means that station can wake up at arbitrarily time instant. We don't need synchronization anymore, okay? And the other property is that there must be many instants in which a station transmits and the other stays silent in order to overcome possible malfunctioning, okay? So, the definition, just to give a bit of formal definition, what we do is the following. For any vector which represents a protocol, we compute all the possible shifts, which represent essentially all possible time instant in which a station starts transmitting, okay? And now we compute the adversary, that is the possible pattern of transmission of the other k-1 stations. And this is essentially the OR of their protocol, okay? Now what we require is this stronger property. For any protocol, for any cyclic shift of the protocol, so the station can start at arbitrary time, for any pattern of the adversaries, k-1 adversary, what we have is that the number of ones in common is not too much. Is at most some factor of the number of ones in the shifted protocol. So essentially, this means that for any possible time instant in which the stations wake up, and for any possible choice of the adversary, at least one minus alpha of the transmission do not conflict with the ones of the adversary. And so this means that there are many instants of time in which there can be a success. There are similar concepts in the literature. Terrible. Okay. Anyway, that's okay. I have to talk faster. Anyway, strongly conflict avoiding codes and so on and so forth. I'll skip the example, I'm sorry. So I just give you the result. The result is that we can construct, I mean, this is an algorithm, not existential result, in which we can construct that gives protocol of this length, and is the bound good or bad? We can also prove a lower bound, and you will see that there is always this pesky logarithm at the denominator between the upper and lower bound. That's okay, that's the life. This is a result that I have found with my collaborator, Adele Rescigno, Roberto Bruno. Anyway, we also give some nice trade-off between the total transmission time, the length of the protocol, the energy consumption, which is the number of instants in which the session really transmit, and the fault tolerance. The main open problem in the area. The main open problem in the area is what I said before. Close the gap. I mean, it's really a shame. I mean, this was all posed more than 40 years ago, still open. I mean, I think that some young people should try and try to solve the problem, because it's, if I can give a conjecture, I strongly believe that this is the truth. And the reason is the following. All the construction that obtain this bound are obtained through probabilistic argument. They just randomly choose code word, and they show that with high probability there exists a superimposed code with this length. But the probabilistic method very, very rarely gives the optimal construction. I mean, it's, I don't believe it. I mean, and there are many, many reasons for that. Another problem is to find other algorithm for other variant of the superimposed code. Deterministic algorithm is not easy. Anyway, since I ran out of time, I just explained the application of superimposed code to data security. First, the definition. What is a frame-proof code? A frame-proof code is quite similar to superimposed code, only we speak now over an alphabet that is not binary, an arbitrary alphabet. And the property is the following. For any column, and for any other k column, there always exists a row in which the symbol of the first column is different from all the others. Frame-proof code were introduced by Bone and Shaw in the context of protecting digital data. And the idea essentially is the following. I will explain the idea. Suppose that you have a document, for instance, a photograph or whatever, some digital document that you want to distribute, okay? That you want to sell. But you want that only legitimate copies stay around. So the idea is to insert in this digital document a signature. A signature is simply a string over certain alphabet. Okay? This means that this is a legitimate copy of the document because there is the correct signature. Okay? But you don't want that dishonest people fork the the signature. So you do not want that dishonest group of people, by colluding, can reconstruct the signature of another honest user. Okay? Let's make an example as we'll see, because frame-proof code prevents that. Suppose that we have this code and the column are the signature. In this case, we are lost because if the two blue people collude, as you can see, each part of the signature of the red guy is contained in the blue part, in the blue column. So they colluding can reconstruct the signature. So in this case, instead, as you can see that in the second position, the signature of the red guy cannot be reconstructed by the blue coalition. And so this is essentially because the code is a frame-proof code. Since I ran out of the time, I say that this is many applications. The problem is always to find codes with short signature. And we were able to prove a bunch of construction, upper and lower bound, that improves the bound in the literature. Essentially, the main tool is the fantastic Lovaas local lemma, at least in the version, in the deterministic version given by Moser and Tardos. And this is a result that I have proved with my two collaborators, Marco Dalai and Stefano Della Fiore. Again, the problem is close the gap. There is always this logarithmic difference between the upper and lower bound. Okay, I'm done.
So I think we have time for questions, if there are questions. I would, there is one, yes.
Thank you for a very nice talk. You mentioned in the cyclic version that you want to have not just one row with superimposed property, but many of them. What is about the classical problem? If I want to have at least lambda columns which have this property that their one is unique, does it change the problem? Or?
Not too much. It becomes a little more difficult, but that can be solved with the same tools. Only you get a longer length because the property is stronger. But the tools that allows also, in fact, the situation that you described finds applications mostly in this modern one-bit compressive sensing, in which they need this property expanded over group of column versus another group of column. And there are several papers on the transaction of the IEEE that study this problem.
So what would be the title for such a paper?
Yeah. Well, there is a paper of mine is on these giant families or something like that. I will take.
I can write you.
Yeah, I can write. Yeah.
Okay, thank you.
Are there further questions? I would have one simple question. In your protocol that you have shown for the multiple access channel, when these three users try to access the channel, so once I have successfully decoded one of the packets, I could try to subtract that from some former received superposition, right? There are some protocols where you do this type of successive interference cancellation. Are there codes for those scenarios developed as well?
There are, because actually in this case, what you need in order to do this subtraction, that a limited number of stations try to transmit at the same time, because if there are too many, you cannot do this subtraction. But if there are few, you get a successful and you can subtract from this. If you control the number of, let's say, collisions. There are codes about that. Yeah. As I said, there are many variants.
Super, thank you very much.